Hello everyone. Now I'm going to present the work Autonomous Capability Assessment of Black Box Sequential Decision Making Systems. This is a joint work with Roshan Karya and Siddharth Srivastava. Nowadays we see sequential decision making systems being used in wide variety of settings where they are expected to work with users who are not experts in AI. Now, these users would want to give multiple tasks to these AI systems and they would want to know what these systems can or cannot do safely. Hence, these systems should make it easy for their users or operators to learn how to use them safely. But we have to keep in mind that these systems will most likely be black boxes as their manufacturers wouldn't want to reveal their internal working. So ideally, we would want to support some sort of personalized assessment for these black box AI systems. In this direction, there is already some work on learning probabilistic models of AI systems using the observed traces of that AI system interacting with the environment. These learning setups use only passive observations and hence they can end up learning incorrect models as they cannot guarantee to capture all the transitions. There are a class of methods that learn symbolic models by sampling transitions using some predetermined sampling strategy. These methods try to overcome the limitations of passive observation-based learners by having some control over the process of collecting the samples. But then they can have lower sample efficiency, meaning they might need large number of samples to learn the models. Or sometimes they can fail to capture some of the transitions depending on their sampling strategy. And finally, there is a class of autonomous assessment methods they currently work only for deterministic settings. So, in this work, we try to address these issues and develop an autonomous assessment system for sequential decision making systems that works even for stochastic settings. Now, I'll walk you through a high level overview of our proposal setup. So, here we have this user who wants to understand the capabilities of this black box sequential decision making agent or SDM agent for short. So for this, we propose this query-based autonomous capability estimation system called CASE, which takes two inputs. The first input is the concept vocabulary of the user in the form of logical predicates. So these are the terms that the user understands. The second input is the name of the capabilities that the black box SDM agent supports. Using these two things as input, CASE generates queries which it asks to the SDM agent. The SDM agent then can answer these queries using a simulator. After multiple query answering sessions, Case comes up with a capability description for each of the capability of the SDM agent. Now these capability descriptions are in PPDDL form. I think most of the audience here would be familiar with what PPDDL is. It is essentially a probabilistic PDDL. So for each capability, we have a precondition that is the formula that must be true for that capability to execute. And effect is actually a set of effects where each effect is a formula that becomes true on executing that capability, and each of these effects has an associated probability with it. Now the algorithm for case works in two phases. In the first phase, it learns a non-deterministic model, meaning it learns all the possible effects but not the probabilities. And in the second phase, from this non-deterministic model, it generates a probabilistic model, meaning it learns the correct probabilities for each of the set of effects. Now we'll first see how case learns the non-deterministic model. So given the set of capabilities and the set of predicates that a user understands, we first generate an abstract model. In this model, we do not know what is the precondition or effect of each capability is. So each of the predicate in the user's vocabulary can appear in each capability's precondition or effect in three possible forms: positive, negative, or absent. Meaning it can be a positive precondition or positive effect, a negative precondition or negative effect, or it can be absent in precondition and or effect. So we represent these entities using n1 to n8, and then we can choose to find the correct form of them in any order. So here we'll first choose to go with n5. So now we are trying to figure out what is the correct form of hash charge in the effect of pick item capability. So we get these three abstract models, MA, ME, and MC. So here in MA, hash charge becomes false on executing this particular capability. Whereas in MB, hash charge becomes true on executing the pick item capability. So we take any of these two models and then generate a distinguishing query. Meaning, if we ask this query to an agent initialized with MA and to another agent initialized with MB, the answers of both these agents will not match. We'll shortly see what we mean like for this query and answers are. But what we do is we reduce the query generation to a form planning problem. So what we do is that we get an initial state from a simulator. So basically it is in a low level form, and then we convert it to a high level state representable using the user's vocabulary. And starting from this state, we generate a policy as a query. Now to generate this policy, we take the two models that differ only in one predicate in precondition of effect. So here MA and MB differ in how hash charge appears in their effect. Now we generate a consolidated capability using these two models, which has its precondition set to disjunction of MA and MB's precondition. So for each predicate, we have two separate copies, one keeping track of how MA is going to modify it, and the other keeping track of how MB is going to modify it. Right. So we have the precondition that either MA should be able to execute this capability or MB should be able to execute this capability. And then we have three possible effects. So first, I'll give intuition why we are doing this. The basic idea is that by following this policy, MA and MB should end up in states that are not same, or they should end up in states where the same capability is executable according to MA but not according to MB or vice versa. Right? Yeah. So coming back to the pick item capability, in the consolidated capability, we will have three possible effects. The first two are trying to capture the fact that precondition of only one of them is satisfied and not the other one. So if we reach this particular state, we'll reach our goal. The third one says that if preconditions of both MA and MB are satisfied in that state, then we will apply effects to both of them. And by solving this particular font planning problem using any generic font planner, we can generate a policy that will serve as the query that we will ask to the agent. So we ask that query to the agent and then we match the answer of that agent with that of MA and MB's answer. And using that, we can reject one or even both of the models. We do this process and this gives us a non-deterministic model for the agent. Then what we do is to convert this non-deterministic model into a probabilistic model. For each of the query, we ask that query multiple time to the agent, and based on the collected effects, we just do a simple MLE to get the probabilities of each of the set of effects. Now we'll move on to the results. So we were able to show that the models that case learns are sound and complete with respect to the sequential decision-making agents transition model or transition system. And we are also able to show that in the limit, case learns models with accurate probabilities. Now moving on to the empirical evaluation. We performed the empirical evaluation on five sequential decision-making agents, and we compared the accuracy of the learned model of our approach with that of glib. And we did this in form of variational distance, that this captures how many of the sample transitions using our approach and the ground truth model matched, and the same for glib. And here are the results. We see similar trends for all five sequential decision-making agents. I'll focus on elevator control agent. Here we can see that it takes much less time for case to generate a model that is very close to the ground truth transition system T dash, whereas glib G and glib, the two variants of glib, were not able to learn a model that was as close to the transitions of the SDM agent as Case was able to. So this brings us to the end of the presentation. In case you have any questions, please feel free to ask me after the video, or you can also email me at verma.pulkit@asu.edu. Thanks a lot for listening.